Okay, welcome back to our last section of the quarter. This being also the last section of chapter 5. And I think I think this is an interesting section. It goes right along with the 5.5 section, law of sines, in the sense that we're going to solve any triangle. So we were given for law of sines the AAS, the ASA, and the SSA versions. The law of cosines deals with other given information. You might understand, you might guess what those other variations are. But as with the law of sines, I want to prove a triangle first. Or not prove a triangle, I want to prove this theorem and what the theorem actually looks like. So we're going to start with, be helpful if I drew a triangle, if I could draw here. So we're going to start with an XY axis basically. And we are going to draw a triangle. Like so. We're also going to draw a height in here. Okay, so this over here is A, this is B, this is C. This is obviously the point 0, 0. This is the point C, comma 0 because it's the side opposite from C, it's length C. We're going to call this point D only to have it as a point D. Heights are right angles. This is A, this is little b. Now we're going to let this point C up here be the point P, Q. And there's going to be some questions that we're going to ask here. So you might have seen it just a second ago, but the first question is, I want to write two different expressions. One expression for P squared plus Q squared, and one expression for P in terms of B and angle A. So it's probably a good idea to know where P and Q are. Since this is the coordinate PQ, this is to the right P units and up Q. And for the first thing here, P squared plus Q squared, that kind of makes me think Pythagorean theorem. So P squared plus Q squared is, well, in this case, P squared plus Q squared, oh, that's going to be B squared. Now the other thing for P in terms of B and angle A. If I look at P and B, I have side adjacent and hypotenuse, which means I can use cosine. So I'm going to do a little scratch work up here. So cosine of A is equal to P over B, but I want P by itself, so I'm going to multiply. So I'm going to get P is equal to B cosine of A. And we might have noticed this kind of looks like a height, only instead of sine, we're using cosine. That's actually almost the same thing. All right, so that's the first question. So that's like question A. Question B here is going to say, okay, find A squared in terms of C, P, and Q, and expand your answer. Okay, so this is question B. So I have A squared. So A squared is a hypotenuse, or A is a hypotenuse of this other right triangle. So I have A squared equals, I know I have Q squared plus, well, what's this distance? The full length is C, the little length is P. So this is C minus P. So plus C minus P squared. So we want to expand this. If I FOIL this out, I get C squared minus 2CP plus P squared. Okay, so that's this question. Expand your answer. I now have A squared in terms of C, P, and Q. But we're going to use question A, and we're going to use those results to find an expression for A squared in terms of just B, C, and A. So I know this is super important, so I'm going to change colors here. Let's go to red. A squared equals. Well, look here. I have Q squared plus P squared. Well, I said Q squared plus P squared is B squared plus c squared minus 2 times c, and I know p is b cosine a. Oh, look at that. Now, you didn't know what we were looking for to begin with, but we are actually, this is a proof. This is a geometry proof to prove the law of cosines. Using some random triangle and then looking at the height. This right here is the law of cosines. Notice A, B, and C are just sides of a triangle with an angle. So this is one variation of the law of cosines. This is where a squared here. And let's just kind of jump into what they look like outside of that one there and how we're going to use them. So the first thing is, this is for your other two versions, the SSS or the SAS. Notice, I'm going to mention this so I never want to see it. AAA never works. If you remember, AAA from geometry represents similarity. That means if I told you you had angles of 30, 50, and 20, I can't do my math right. 30, 50, and 100, okay? There's no way to tell me the side lengths of these triangles. So there's nothing I can do with angle, angle, angle. So that is a nothing. So we're looking at side, 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 and side, angle, side. So now we can solve basically any triangle. And there's the one that we just created, a squared equals b squared plus c squared. And the other variations are just the changing things around. So I replaced a squared with b squared, so I just swapped, basically I swapped their spots. And then I did the same thing with c with a. All right, now this is good when you're looking for a side. Well, you're not going to look for a side with side, side, side. So this is good for side angle, side triangles. And just like the law of sines, there's two variations. This is solving for cosine C, or cosine A, sorry, for the first one. You would just subtract b squared, subtract c squared, and divide by negative 2bc. So that's pretty straightforward that this ends up being another variation. And same thing for all three of those. And since I have an angle over here by itself with cosine, this is good for side, 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 because notice the right side of the equal sign only has sides on it. So these are good. This is a good setup for side, side, side triangles. All right, so let's look at a couple examples here. First one given these two things here, or three things, sorry. If I was to draw some random triangle with A, B, C, 20, little a is 11, little b is 5, you ask yourself, can you solve this triangle using law of sines? Well, no, because this is side, angle, side. But I can use law of cosines. Now, law of cosines is very interesting because all you have to do is the law of cosines once. And as soon as you've done the law of cosines once, you can use the law of sines. And then once you use the law of sines once, usually you're down to the point where you get a really nice angle. You're looking for an angle usually. So you can do the triangle sum theorem. So here's what we need to do. We're looking for a side first, because I can't look for this angle. So we're looking for a side first. So I look at c squared equals 11 squared plus 5 squared minus 2 times 11 times 5 times the cosine of 20. If I take the square root of that, I get c equals, and you could do this all at once, by the way, square root. I'm just going to do it all at once. 11 squared plus 5 squared minus 2 times 11 times 5 times cosine of 20. I make sure my calculator's in degrees. I hit enter, and I get c equals 6.53. Now, here's where things get a little interesting. always look for the smaller of the two angles first. And it has to do with the fact that now you can use law of sines. And law of sines just always works better with the acute angle. So I know this angle B is smaller than A because of their opposite sides. So I'm going to find B first. And I'm going to say sine of B over 5 equals sine of 20 over little c. And I'm going to use little c in my calculator. So I'm not going to bother getting a decimal in there. So B is equal to, just like we did yesterday, sine inverse of 5 sine of 20 over little c. And I get B equals, all right, sine inverse of 5 sine of 20 divided by answer. I get 15.18 degrees. And then all I have to do is do 180 minus 20 minus that answer. And I get this angle here is, angle A is 180 minus 20 minus angle B. And I get approximately 144.82 degrees. Remember to do accuracy here. Use good accuracy, very, very accurate, okay? So use the store button on your calculator or use the ANS button on your calculator. All right, another example here. I think I have a side, side, side version. Oh, looky there, side, side, side. All right, I get A, B, C, 9, 7, 5. And since I'm looking for an angle, I'm going to find an angle. And it shouldn't matter what angle you look for first, but I always like to just start with the smaller angle. Let's think about that for a second. Cosine inverse is in quadrants 1 and 2. Which means that's the only places that angles should come up anyway. So it doesn't matter what angle you start with first for law of cosines. If you want to get the big angle out of the way, go for it. Let's just do that. Let's say, okay, cosine of A equals, because A is the bigger angle, is, let's see if I can remember this, 7 squared plus 5 squared minus 2 times 7 times 5 all over, oops, sorry, not paying attention to myself. It's going to be A squared plus, oh, be a good thing if I just wrote this down, huh? Seven squared plus 5 squared minus 9 squared all over 2 times 7 times 5. There we go. And cosine inverse of this. Be very careful with parentheses here, because if you don't use parentheses correctly, you're going to get a wrong answer. So make sure your entire numerator is in parentheses, divided by your entire denominator in parentheses. So 49 minus 25, sorry, plus 25 minus 81 divided by 70. I get A is 95.74 degrees. And now that I know an angle, look at this. I can go straight to law of sines, because now I'm given angle side side, or yeah, angle side side. So, and it's only one triangle here. I can't create two triangles from this, by the way. So you guys will enjoy law of cosines. All right, so let's see. Sine of 95.74 over 9 is equal to sine of C over 5. So C is approximately equal to the sine inverse of 5 sine A over 9. So C is approximately, I'm going to store that last answer for A. So store alpha A. Then I'm going to do sine inverse of 5 sine answer divided by 9. I mean, C is 33.56. Then I'm going to do 180 minus answer minus A. And I get 50. So B is 50.71 or 70. And always do just a quick double check. Does that make sense? Sort of idea here. Does it make sense? Do these three numbers add up to 180? They better, because that's how I got them. The 9 side is across from the 95. The 7 is across from the 50, and the 5 is across from the 33. So it kind of looks good. Okay, last one here is going to be a word problem, obviously. The bases on a baseball diamond are 90 feet apart, and the pitcher's rubber is 60.5 feet from home plate. Find the distance from the pitcher's rubber to first base. Now, some people don't exactly know what I'm talking about here, but we're looking at a baseball diamond. That's an ugly diamond. But here's first base. Here's home. Here's second, here's third, and the pitcher's mound, or the pitcher's rubber, is where they stand, is right in here. And some people think that this is a right triangle. It's not. This is not a right triangle. The pitcher's mound is actually forward or backwards from first base. I forget off the top of my head. But I am told that the bases are 90 feet apart, and from the pitcher's mound to home plate is 60.5 feet. And then you need to figure out, what do you need to figure out? Find the distance from pitcher's mound to first base. So you need to figure out this. But some of you are like, well, I'm not given enough information. You are actually, because the bases, when you reach a base, you turn 90 degrees. So right down here, coming straight down, this is actually a 45-degree angle. Be very careful that this is not 90 also. The home base, or the pitcher's mound, is not 90. So now I'm given enough stuff so I can say x squared equals what? 90 squared plus 60.5 squared minus 2 times 90 times 60.5 times the cosine of 45 degrees. And I do a quick math here. Square root of 90 squared plus 60.5 squared minus 2 times 90 times 60.5 times the cosine of 45. And I get 63.72 feet. Nice and easy. All right, last little thing that we can do with law of cosines, and actually it weirdly doesn't have anything to do with law of cosines, but they're actually really, really cool formulas. And they're formulas for area. So if you're given a triangle that gives you side angle side, we have this formula for area, and it's one of the three. It's just depending on what you're given. Okay, so it's the two sides and the included angle. The area of any triangle in this form. So if I said, here I've got 3A5, and this is 10. All I have to do is 1/2 times 3 times 5 times the sine of 10. And that should actually kind of make sense, because we can find the height of the triangle using b sine of A, and the height of the triangle actually ends up being 5 sine of 10 times 1/2 times the length of the base. So it's just our basic 1/2 BH formula, just looking at it in trig form rather than needing to find the height. But the next formula is super cool. This is Heron's formula. I don't know who Heron is off the top of my head. And the thing is, if you're given 3 sides of a triangle, if you're given 3 sides of a triangle, you get this really nice formula. I'm going to rewrite this a little bit because I didn't have the square root button. It's s times s minus a times s minus b times s minus c. And s is just it's called like a semi-average or something like that, where you add up the 3 sides and divide by 2. And that's what s is. So if you, sorry, the proof is somewhere in your textbook, but if I was to ask you the sides 13, 15, and 18, I would say s is equal to 13 plus 15 plus 18 divided by 2, which is, really quick, 13 plus 15 plus 18 divided by 2 is 23. So I could just say area equals the square root of 23 times 23 minus 13, which is 10, 23 minus 15, which is 8, and 23 minus 18, which is 5. And that's such a cool formula because it doesn't require really any trig, and it doesn't really require any angles. It doesn't require a height. There's no half involved. It's really super cool to me. All right. So those are the little ones. Really remember the whole, basically the most of the assignment is based off of law of cosines. All right, so have fun with this. I will see you guys tomorrow, and I hope you guys do well.